Structural and optical characteristic of MgZnO nanocrystal films doped with indium element for ultraviolet photovoltaics. MgZnO semiconductor materials have garnered significant interest for optoelectronic applications, such as highly transparent conductive windows for solar cells, display panels, ultraviolet photodetectors, and ultraviolet light emitting diodes. It's important to note that ultraviolet devices play a crucial role in tasks such as ozone detection in the atmosphere, monitoring water purification, and photocatalytic reduction for pollutants in water and air. Additionally, magnesium alloys offer benefits such as non-toxicity, biodegradability, inhibition of biofilms growth, and the promotion of harmful dye degradation. By forming magnesium alloys with varying magnesium content, larger bandgap windows can be created for zinc-based devices. The bandgap of these alloys shifts towards the visible to ultraviolet range depending on the magnesium content. Increasing the magnesium content in zinc films within the range of 0 to 20 atomic percent enhance transmittance in the ultraviolet range for 3.37 to 4.0 electron volts at 300 kelvins, while maintaining the worst crystalline structure. This tunability of optical bandgap in magnesium films makes them ideal for ultraviolet optoelectronic devices. Magnesium doped with indium films were prepared by ultrasonic spray pyrolysis on quartz and silicon substrates. A solution of methanol, acetic acid, and water, 80-10-10 respectively, was used to dilute 0.2 moles of zinc acetate. The prepared solution was sprayed on the quartz and silicon substrates, heated to 400 Celsius degrees for 60 minutes, with a nitrogen carrier gas flow of 4 liters per minute. Assessment of magnesium doped with indium samples was studied. Interval of 99% magnesium acetate tetrahydride was applied in a 10 and 20 atomic percent content as magnesium precursor and indium contents of 0 to 5%. After tar films were deposited at thermal annealing treatment at 350 Celsius degrees for 3 hours in a nitrogen flow of 8 liters per minute was done. The morphology, optical, and structural parameters of films of magnesium with different magnesium composition and different indium contents have been studied. The morphology observed in these samples were hexagonal grains with grain size ranging from 30 to 400 nanometers, diminishing as indium is incorporated into the lattice. X-ray diffraction diffractograms revealed a worse structure, with magnesium 10% samples displaying higher intensity compared to those with 20% magnesium content. Additionally, the energy gap for magnesium 10% samples exceeded the highest value, while this value generally decreased at 20% magnesium samples. Overall, it was observed that a 10% magnesium content facilitates the enhancement of crystalline quality in the films, leading to alteration in their structural, morphological, and optical properties. EDS spectrum analysis revealed the presence of indium, zinc, magnesium, and oxygen in two distinct sets of samples with magnesium concentration of 10% and 20%. On the other hand, the transmittance exhibited a sharp absorption edge for all samples. In addition, a noticeable shift occurred at the fundamental edge for variant concentration of indium, exclusively observed in magnesium 10% samples. This shift was less pronounced in samples with 20% of magnesium. Resistivity increases monotonically with rising magnesium contents. That correlates well with the concentration increase of host vacancy type defects. Note that group 2,6 semiconductor materials such as zinc oxide and magnesium zinc films with indium less equal than 0.5 atomic percent typically have n-time electrical conductivity. The N-type conductivity of undoped zinc oxide and magnesium zinc films is due to the high content of shallow donors, such as the complexes of interstitial zinc atoms, zinc nitrogen oxide bonds, or hydrogen atoms in oxygen sites and hydrogen oxide bonds. Conclusion: X-ray diffraction analysis shows Bursite structure. Moreover, the shift of peak 002 suggests a relationship between elastic strain, not shown here, and electrical resistivity. In addition, when indium is 4% for both magnesium content, the minimum of resistivity at min size is achieved. However, the maximum of energy gap is reached at 3 atomic percent when maintaining an optical transmittance of 85 to 19%. The increase in indium composition is accompanied by a decrease in electrical resistivity. Magnesium zinc films doped with indium are interesting for optoelectronic applications in ultraviolet light emitting diodes, ultraviolet photodetectors, or high transparency windows for zinc-oxide-based devices. This work was supported by SIP, IPA, Mexico, Project 2024-0156 and 2024-0786.